Okay, and I think we're ready to get started here. So we're very lucky to have JB Pauline here with us. He was so kind as to offer to talk about data sharing, sort of a lot more technical stuff yesterday and today, to more theoretical and statistical aspects of reproducibility. So getting full coverage of various aspects of reproducibility. And he'll talk, I think, both about statistical and also social aspects of reproducibility in this talk. Take it away, JB.
Thank you. Let me try to put the Zoom window in the same place so I can see you a little bit on Zoom if I switch windows. All right, let's see if that works. Yeah, okay. Well, thanks again for the invitation. I think it's always a great pleasure to be here. This talk is a little bit of a weird one. I think some of it you've heard before, and it's actually quite good that you hear it again. So I'm not bummed by that. Some of it is going into even details that you might think, okay, that's too much detail for me. I don't want to hear about that. At the same time, this is more to say, hey, those things are not that hard, okay. And some of it, if you are a statistician, or if you have worked with statistics quite a bit, of especially classical statistics, you will think, okay, I know that, okay. So that's not for you to just do your emails. That's fine, But yes.
You need to share your screen.
I do need to share my screen. That is correct. That should be better, hopefully. Thanks. Let me try to move the other way. All right. And as usual, please just interrupt. I'm guessing I might be looking at the Slack or but just don't hesitate to stop me, because that's I way much prefer to make that of conversation than. This is a slide of my lab. I just want to say, thank you to all the people over there. We've got a fantastic team that is making it possible to do a lot of things that I wouldn't have dreamt of. And I will start a little bit, I guess, within the kind of a bit like what Russ was doing. And again, I share some slides with Russ. I don't know if I stole them from him or the opposite, but I will just share that reproducibility story. Then we'll go into the statistical aspect of some of the problems, and then as well as the sociological aspects and the So the story that I usually teach and start, I really love it. I think it's such a important story to know about, is the Potier et al. Story that yeah.
Sorry, I'm just gonna make sure that this is on.
Oh, is it on? Is it not me not speaking?
I'll just put it a little closer.
Oh, wow.
Sorry about that.
This is frightening. Okay, so the Potier et al. Story is a very interesting one. So it was a very successful researcher that had a fantastic idea that there is a bank of cells that you can test for sensitivity to drugs, and they had the genome of those cells, and what they did is to look at what cells were reacting to some drugs, and then look at the genome of patients, and then thinking, okay, if I can match which cells are reacting to drugs or which are now resistant to those drugs, and then match to the genome of those patients, maybe I can, we can sort of give the better drug to the patient, it was a cancer, yeah. And so it was it was very well published and all those things, this method was attracting a lot of attention when, especially when there's a big, paper in the nature of those things, and so two biostatisticians at the time, Bagley and Combe, had their colleagues in medicine and biology thinking, okay, that sounds like a fantastic method. Can you help us? There was a bit of a PCA and a PLS analysis and those things, and can you help us redo that kind of a study? And So those statisticians started to dig into the paper, and thanks God, the data were actually available, which is not like the usual thing, because I think NIH required that those cells where bank cells were available and those things, and so they kind of started to try to replicate reproduce the paper, and after a month they couldn't, and then they started to think, okay, what could have gone wrong? And they did a lot of kind of a backward analysis of, okay, what if the authors did that, or what the author did that, and so on. And eventually they found that they couldn't actually replicate, but they could find why they couldn't replicate by looking at what kind of mistakes were done during the analysis and the processing of those data. So then they tried to publish it, and what happened is that they tried to publish it in the original Nature Medicine or kind of journals that Nature Medicine was not interested. They said right away rejection, test rejection, there's and they eventually sent that to a applied statistical journal, which published it right away. Okay, that is super important. And it was super important because at the time there was starting to be clinical trial on those results. So people actual patient giving drugs that may actually not be corresponding to the fitting aspect. So that was a kind of a wake up call, I think, for a large community. And then I think if you hear about that story, you will hear about later on. I think the original authors tried to cover up. So they said, okay, no, we didn't do that mistake. It was because of X, and so on. So and then there was kind of fraud involved. I really don't want to talk about the fraud thing. It's I think it's very it's very rare. I think in our kind of it's not inexistent. I mean, you will hear about occasionally you will hear about a fraud in science, and that it does happen. It's just it doesn't happen, but I think it's very rare. I think the most important problem is that the mistake that were done was just genuine mistake. So Baggett and Combe called that their forensic analysis, because it was trying to find what happened to the post-mortem analysis of that paper in some ways, and they said it was a poor documentation, irreproducibility. Even with well-meaning investigator may argue for drugs that are contraindicated to some patients. So they basically say it was just poor documentation and some mistakes. And they also conclude that the most common errors are simple, and the most simple errors are common. And you've seen some of those examples already. And I think again, there's this feeling that we are not setting ourselves in terms of the test aspect. And I love the fact that more and more labs actually are starting to do, okay, the first thing we do is simulate data and see how that goes. Or the first thing we do is permute the label and see what we get And I think the more and more labs are kind of setting those scientific tests. You've heard about continuous integration and unit testing framework. I think there's a mindset of a framework for scientific testing that is not often yet there. And the reason why it's not often yet there is that it takes time. It takes effort. It's kind of it's a little bit of a more to be done. The Amgen replication is another one that has now a follow-up study that has been published in eLife recently on and it's basically was the idea that there was a little pharma that tried to replicate 50 very high-profile journals. They were Cell, Nature, 3 very high-profile journals. And they picked up those papers that had groundbreaking and very fundamentally changing advancing the field. That pharma was thinking, okay, we are going to redo these experiments and build on the top of those things. And so they at the end, so what they did, the process is important. When you talk about those things, I think it's really important to look at what is the process and what is the entire things. And sometimes those stories are actually not very true, because there are some of those key details are kind of put under the carpet. But here they tried to reproduce in their own lab. Then they contacted, when they couldn't, they contacted the authors and say, okay, how can you help us do it? And when they couldn't reproduce the results, they went to the original authors' laboratories and tried to reproduce those things in their wet lab. And at the end of those 2 or 3 years of, it takes so much time to do these sort of things, and at the end of those few years, they concluded that, only, 6 out of those 53 was really things that you could. Sorry, folks. I don't know why my Israel kind of dropped down and. Yeah, so so I don't know when I was cut on Zoom, but basically the issue of not having enough information in the paper is was one of the things, but the actual fact is that even if you ask the authors and so on, it's I mean, replication was not good. So NIH was thinking, okay, we have a little pharma that is using probably billions of dollars that have been put in NIH kind of grants, and then and those things are to make economic growth and scientific progress and all those things, and it's it's a very dark kind of situation. So soon after that paper, there was our experiment. It was the NIH plan to enhance reproducibility, and that's now 10 years ago. And so the question is, what has changed fundamentally or not? Is the question. It's been 10 years, and I feel like, so I was already senior researcher at the time. I feel like there has been a lot of progress, and I think that's there's the recent NIH mandate for data sharing. There's a much more awareness and so on. However, I would say, we talk about those things in this type of setting and audience, and students are very well receptive and those things. I would say the general kind of a culture of neuroscience and has not changed that much. There's small little nudge and progress, but there's no kind of a revolution of okay, we need to do something different. That doesn't happen. Okay, so I'm going to dive into a little bit of a statistical aspect, and please bear with me. Some of it is very simple, some of it is a little bit more complex. But I want to also set the framework of the statistical, things that we do in a more kind of a general, almost like epistemological aspect of the work. So I've been interested in data analysis and statistical data analysis for a long time, and I've just plotted this recently. This curve that one of the things that I always thought, okay, there are statisticians that are developing superb methods and very useful methods. And who is actually taking them up, and who is actually applying those methods for actual data, for actual studies, and the ones that are you see that are prominent in the big papers and so on. And sometimes it happens, but it's super rare. And the thing that I'm seeing in the lecture today, yes, no, oh, sorry, there was a question. The thing I'm seeing these days is that there is a kind of a plateau and even possibly decrease of those statistical methods that are being published. And I think it's partly because everything has been taken over by deep learning and machine learning aspects, and partly because people have been moving for other things, and there's a dwindling, I would say, the classical type of methods that are doing, and it's a big split between communities. It's those statistical communities, they really have go to statistical meeting. And you see that the applications are really often an excuse, it's oh, give me the data. It doesn't matter which data. It doesn't matter what it's I'll play with that, and I work on my algorithm, and that's okay. So that split of community is interesting epistemologically. I think it doesn't always the case, but it's often the case. And again, many of the good techniques are, that are developed in Neurohack or SBI, or MICAI is now completely deep learning. So forget about the statistics in MICAI, they don't exist anymore. But all those good techniques are generally, I mean, 95%, I would say, if I have a guess, are actually never used in a and I would love to have counterexamples. If you're telling me, we've looked at that paper in the statistical literature and in my lab, and we actually applied that new fancy method to those data because we thought that was really good. I would love to hear the stories. I think they are very rare, very rare. The other thing is that, and something that you're learning here at New Academy quite a lot, is that those methods and those developments are generally not packaged. They're generally super hard to install, or super buggy, or very poorly documented because there's no incentive. There's no you're a stats, you're a stat person, you do some of your research on statistics, and you're publishing in those kind of applied mathematical kind of a set of settings. But there's no incentive to make that thing useful and used by especially the neuroscience community. I think that's so. In 2011, almost 15 years ago, there was this very good paper that says, okay, the general linear model is not a technique we should be using for fMRI analysis, or and last time I looked, 90% of the actual analysis and things are done with the GLM. And I'm not saying it's a wrong thing to do. I'm just saying that there's really that split of community and things that is interesting to at least hear about and open your eyes about. The last time I look as well, even if machine learning and deep learning is actually growing and interesting, and very, very large amount of tests are done with t-test and ANOVA, I don't know how many of you have actually work on things that are not going to be in that framework at some stage, or part of the studies is not going to be in that framework at all. I think very few people, right? I mean, most of you will have to do those classical statistics just to reinforce, or to at least some of the and I'll talk more about that the problems that occurs with that. So the other thing is that, which is also interesting, is that in those massive amount of papers and articles online, there seems to be more and more articles and more, the growth of the number of papers is quite dramatic. If you look at just the number of published articles online. However, there's this nice study that is very interesting to look at, which is basically says it's looked like the number of papers is actually not helping the advance of a scientific field. And so that article is saying, we're completely flooded with papers, but that doesn't seem to be, making the field go quicker, or those. So they looked at a number of different scientific fields, and that's their conclusion. Yeah. So let's dive a little bit in the kind of a very classical way of how biology and medicine have been working with, which is the statistical kind of framework. So there's this quote that says that we are inclined to think that as far as a particular hypothesis is concerned, no test based upon a theory of probability can by itself provide any valuable evidence of the truth, of the falsehood of a hypothesis. Who do you think has said that? Let's give you a guess, or at least what kind of person, No idea? Online number? Neither? Come on, Ariel, do you have an idea?
Yes, I do.
You do, you've run me before. Yeah. Anyways, it is actually those father of the statistical testing hypothesis framework. Of course, Fisher is the grandfather, but those statisticians who actually formalized properly that framework, where Niemann in person, and And those are the ones that say, hey, don't use that for like hypothesis testing of that is not the proper framework for that. So and then you look at the literature and the field, and then everyone is using it, and there's no way to stop that, it seems, because that's kind of like this inertia of things. So I think awareness in that domain is still a requirement. Like we're still, I feel like a broken record, but like it's been a long time saying that, and many others than me, so many people, but it still seems to be like warranted that we need to rethink how we do statistics. And in general, the dominant epistemological framework is still a Popperian framework, where you think, and Popper was specifically interested in what is science, what is not science, and it's not that's such an easy question, really. And he came up with that framework where if it is scientific, it has to be falsifiable. If you can't falsify it, it's not a scientific thing. So if you have a belief, for instance, the belief cannot be easily falsified, and that's not science. And that's how you kind of frame what is science and what is not science. I think it's still a very dominant epistemological framework. There are others, and the most famous one, possibly, it's not complete. It's not like opposing this framework, but Kuhn is definitely very well known in the general public, at least as epistemologist. It's interesting to see that if we I think we've still been the scientific community still be very heavily influenced by that framework, and it's still probably the framework that people still believe in. And I was interested in seeing, okay, how that works, how is that kind of implemented in our hypothesis testing framework? Because it sounds to be like the perfect tool to actually do those classifications. So again, most of the hypotheses we work with in the hypothesis testing framework, the classical framework, are the null hypotheses, right? You're rejecting the null. It's really unclear to me, like, if those hypotheses are the most interesting ones. Often, I mean, they are fine to work with, and that they give you some kind of evidence in some ways. But the actual hypothesis that you're interested in is probably not a null hypothesis in the first place. So we're designing a lot of things to reject the null. We're not designing tests to actually reject our actual hypothesis or actual theory. And I think it's an interesting kind of angle. If you can think of what would be the experiment of the test that you would have to do to reject what you think is true is an interesting angle on the scientific project. And actually, there's also the fact that, if you reject the null, you're rejecting often that the fact that one parameter is exactly 0. So the space that you're rejecting with is huge. You can be anything, and then you can have estimators and things like that. But it's a very, very narrow thing to reject. It's just one point, and that's another aspect of this wideness of hypothesis that is interesting. So I want to take an example in traumatic brain injury. In that literature, there's a number of authors have observed that TBI have a physical disruption of pathways due to focal and diffuse injury results in regional expansion, increase in strength or number of functional connection. So TBI is because of that focal and diffuse injury will actually strengthen the functional connection between brain regions. That's one, there's a large number of papers on that kind of a claim, and that's supporting that claim. Hypothesis 2, other studies of moderate to severe brain injury found that white matter disruption during injury resulted in structural and functional disconnection of networks. So there's really two, at a very broad level, because when you go into the details and things can start to change a little bit, but at a very broad level, there's kind of seems to be like two competing theory in the field of neuroimaging and TBI. That's and really it sounds like a perfect framework for saying, okay, we are going to test one theory versus the other, right? And that's okay. Apparently, I mean, I don't know well that literature, but according to that paper, I've got the reference later. there's even those are contrary hypotheses in place. There's been no direct testing of this position against one each other. And you know, in the literature, you find a set of paper on, you know, adopting one theory and a set of paper adopting another theory. And there's apparently very little kind of, okay, let's test this, you know, those things between them. So it's, you know, like it seems like people adopt a framework and then don't, you know, like, you know, use it for, you know, publishing their kind of, you know, some advance on things. And then, you know, like, and because of that, those priors, they will find things often in favor of that framework. But that's, you know, that's it was very fascinating to me to see that. And hypotheses are not all equal, you know. Their quality of hypotheses are very different from different places. And again, looking at that, you know, wideness of hypothesis aspect, exploratory. So we examine the neural correlates of cognitive deficits after brain injury, implementing graph theoretical measures of whole brain neural networks. That's, you know, that is the kind of hypothesis with quotes, you know, like so that sentence is probably taken from an actual paper, like, you know, it's you know, and it's, you know, maybe in an abstract thing like that. Then you have testable association, like, you know. So we have the hypothesis that graph theoretical measure of whole brain neural networks predict cognitive deficit after brain injury. So that's a prediction aspect. And as a parenthesis, every time you can put things in a predicting framework, you are so much better, you know, set than in the classical, you know, hypothesis testing framework. So please work with prediction. I think that is very solid scientifically, and that's you know, it's one of the things you can. It's harder sometimes, but then there's the testable but also falsifiable position. Okay, so we hypothesize that memory deficit during the first 6 months post-injury are due to the white matter connection loss and maintain a linear and positive relationship with increased global network path length. And it's becoming much more precise. And you can start to falsify those kind of things because of the narrowness of the thing, right? And then you can actually add alternative hypotheses and framework to those things. And then you say, okay, hey, if I also find that diminished global path length in individual with greatest memory impairment, that would challenge this hypothesis. Okay, so there you start to have a really good framework where we can think of you know, some you know, testing things properly and falsifying, and also have alternative thoughts if that doesn't pan out and all those things. So I think having thinking of what hypotheses and the least global and vague they are, the better they are, and you know, the more. I mean, and it goes a little bit against the fact that, you know, the more global and general they are, the more like the prominent will be the article, and you know, that's and that is the kind of thing, like, you know, we're all striving for kind of finding things that are very generic and very universal. But the, you know, the problem is that those hypotheses are very vague, and you know, and there's little kind of a substance often on the when they are rejected. All right, so I'm going to go through a couple of things, and again, some of it you have seen, and I hope that, you know, this rehearsal is not is still useful. But by looking a bit more at what is the null hypothesis testing framework. First of all, because we're talking about reproducibility, I don't think we've seen that slide, so I put it in. There's a vocabulary aspect that is not always well established, you know, in the literature at least. This is the one that I think is the adapted from the Turing way, that says that basically we talk about reproducibility when we think about the same data, the same code or the same pipelines, but you know, try to do it again, you know, 6 months after, like, you know, can you reproduce that? We think about the replicability when the same sort of methods or same pipelines are applied to another set of data, and that's a replication. You can replicate on another cohort of things. I think robustness is more when you use different sort of methods, but that they should give you the same result on the same data. So you're trying to see if those results are robust with the variation of the pipeline that should be giving you similar results, right? And then the actual interesting aspect is that in what dimension your results are generalizing into. So there's so many dimensions. Like data and pipeline and methods are just some of them, but you could think of there's acquisition methods. You could think that there's obviously in time, maybe things should be reproducing in time as well. Like there's so thinking about where are the limit of my generalization aspect is the question that you should be asking when you're reporting something. So p-value, I want to try to like warn you again against p-values. I think again, Neyman and Pearson really put that in the right statistical framework. Otherwise, it's a kind of a hack aspect. And they put that in a place where they are used for making a decision. And and maybe in some statistical book you've heard that you shouldn't even look at the p-value. You should just look at whether it has gone beyond the threshold. And and that's p-value is not like an effect size kind of thing. It's not like an interesting thing to look at in that respect. And I'll try to say you why. Again, and what we're doing, of course, is just like trying to protect ourselves from the type 1 error, the false positive aspect. But that's only one aspect that we protect on. We don't protect ourselves on the type 2 error, which is the false negative, and I'll talk a bit about power in that respect. So I traditionally give that little test to the crowd. So let's go through it, and I promise to not put that slide anymore once I've got more than 50% of the crowd that will respond correctly. So we'll see if we're going to reach that level this year. So this is a study where they test the efficacy of a drug with H0. There's no effect of the drug. Against the H1, there is some effect. Let's say if there's something measured that is, and then you look at the p-value, whether it's and then the result is that there's a p-value that is less than 0.05 in favor of that there is an effect of the drug. So the question is, what exactly has been shown? Okay, so I will ask you for raise of hand. I don't know if someone can monitor the Zoom and tell me what happens there. First is H0's false. Who is in favor of that? No, nobody thinks that H0 is false. Okay. H1 is true. No, no one. Okay, cool. H0 is probably false. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, maybe 10. Let decision. H1 is probably true. So the drug is probably like it. It always strikes me that when you say that H0 is probably false, to me H1 should be probably true as well. But okay, so that's how the people react. Okay, it's so both 1 and 2. So H0 is false and H1 is true. I guess no one, if you said no one was for 1 and 2, both 3 and 4, we have both, H0 is probably false and H1 is probably true. 1, 2, 3, 4.
JP, we put up a little poll on Slack.
Oh, nice.
Get everyone to.
Thank you so much for that. Thank you so much for that. Okay. And then the last one is
bomb for none of the above. There's 1, 2, 3, 4, 5, 6, and the bomb for.
Cool. How much is that for none of the above? Anyone in the room? None of the above. Like no. 1, 2. two people for like in the room. And I guess there are people that are undecided a little bit, and like so we can with
the total solution seems to be 3.
Okay. I think 3, 4, and 6 are the usual things. So this is what the medical students that are actually heavily relying on the t-test and the p-values for like some getting information on in their medical field, because the medical field, like there's a lot of this is what so the number of responses. So you see as well. I think we are basically have the same sort of distribution. There's a few for 1 and 2, quite a bit more for like 3 and 4, and then 6, and then a few for 7. Yes, there's a question. No? Okay. And yes, indeed, the answer is 7, and I'll try to explain why. It sounds a bit surprising in some ways, and you're kind of thinking, okay, but what are we showing if that's like a. And the main reason is a bit technical, but also not only technical. It's the main reason is that you have taken some data and you have shown that those data are incompatible with some hypotheses, like but you have said something about the data. You have said something. You have not said anything about the hypothesis. And that's the if the hypothesis was let's say like a probabilistic thing, and we'll show you an example where it needs to be a probabilistic thing, and it was very, very unlikely. Even if you have evidence for something that is unlikely, it's still unlikely. So you're not giving a statement on the hypothesis, and that's a really important thing to understand. You're giving a statement on those specific data under the hypothesis, and I think that shift of mind. It's not a simple thing to like realize, and actually there's a good study on the books that are teaching statistics for psychologists, and in psychology the field is doing a lot of statistics. That study shows that I think 80% of the textbook that are given to students things are presenting this null hypothesis testing framework in a completely wrong way. In the way that you would answer those kind of like H0 is false or H0 is probably false, like and not thinking about what is H0, what is H1, like those and what are we talking about? So yeah, so that's the p-value is the probability of summing a statistic equal or more extreme than the one seen in the data when the null is true. That's what it is. And what is a statistic? It can be anything, right? It's a statistic it's a function of the data. Okay. So anything that is a function of the data is a statistic, like so that's a very wide space, like we are accustomed to the mean or to the t or z statistics, but anything that can be a statistic, like also that framework is actually quite imposing some very behind the scene constraint that you don't actually realize or see often. That you have to have the knowledge of the null, which is that's such an easy thing to have. You have to choose the right statistics, and that's a very specific kind of choice that you're doing. And there's this concept of a frequentist approach that you have to believe that if you were to repeat exactly the same experiment like an infinite number of times, this is how things will converge over the same design, same population samples, same definition, same sampling scheme, all those things should be exactly the same, and you have to like be able to mentally imagine that you repeat that experiment for like at infinity. So you're aware of the Gaussian, that's no problem, but there's a lot of data distribution that are very far from the Gaussian, like and often I'm sure you're aware, like when you look at the data and you look at those distribution, and by the way, this can be sometimes a problem because how much what do you look at is going to go into your testing, and therefore is that double dipping process or not, like so those things are not that easy to resolve. And that's why, again, the machine learning framework is so much more, so much cleaner. But those things, for instance, with an x of 0.05, you got a p-value of 0.02. Like it depends so much of the distribution and those things that it's a quick little aside on the p-value itself. It's an interesting statistic because under the null, it's actually have a uniform distribution. And that's easy to show. I mean, I don't think I will go for that, but you have access to my slide and you can go through the reasoning for that. It's actually interesting because, so that's the reasoning that tells you, so let's not go into that thing because I will go into other things. The p-value has elicited a number of like misunderstanding and errors, and we've just checked that this is still not a very widely known thing. The most serious error is to consider p-value as the probability that the null is true, and that's a classical way of and that is absolutely not what the p-value is telling you. If trials are conducted, so let's do a little quick experiment. Hopefully, we'll get different answers in this one. Let's say trial are conducted with a type 1 error of 5% and with a power of 80%. I will explain more what power but hopefully you know that this is the probability of finding the results if the results are there. Then the significant results always are corresponding to true difference between the treatment compared. So what is the proportion of true positive versus the number of positive that you find in that setting? So you've got 5% type 1 error, you've got 80% power. So you've got some true positive and some false positive in that experiment. What do you think is the proportion of the true positive divided by the number of positive, so true and false positive? Is it more than 90%? Anyone? Between 85 and 95%? No one? 75, 85? No takers? You're going to the extreme. 65, 75? No takers? Someone maybe 1%. Okay, so it's you have guessed not because of those numbers, but because the way I present those things that this is less than 65. So there's 2/3 of those things that are actually only 2/3 of those things are actually true positive if you look at and there's a way of looking at that. You take thousand null hypothesis. You do the there's maybe there's a 10%, and those things will depend extremely on what is the prevalence, right? And so that's the key problem here. What is the prevalence of those true positive in that? So let's say there's 10% prevalence of true positive true things, and then then you go down the path of whether you have a true one. Then if you have a true one, then this is you've got 80% detection possibility. If you have a not a true one, you've got 900 of those things. But then you've got 5% of true that are going to be detected with the 5% type 1 error, right? So if you go down those two lines and you gather those that are detected whether they are false positive or whether they're detected because they're true positive, and then you see that because of the prevalence is fairly low in that sense, and it's going to be even worse if you take a lower prevalence, then you find this is about 2/3 will be detected in that case. So go do those little things to ingest and understand from the bottom up those things. I think it's always little interesting so don't stay vague on those things. I think is my message here. All right, so p-value can indicate how incompatible data are with the specific statistical model. That's true, that's fine. They do not measure the probability that the study hypothesis is true. That's what we've seen. Scientific clinical conclusion, policy decision, they should absolutely not be based only on whether p-value pass a threshold. So that's and I would say scientific decisions are usually made on that. Proper inference required full reporting. So one of the key aspects, and I think it has been now well understood, but still is you see that in the literature, is that you don't report only a p-value, because a p-value is such a agglomerate thing. It has so many aspects in it that you can't actually decide and decipher what has gone to make that p-value that what it is. It has of course some of the effect size, it has the sample size, it has the distribution, it has a number of things. So basically the message is you report everything. You report and I think I've got I'm putting that message below as well. So it doesn't measure the effect size, and that's or the importance of the results. That's doesn't provide a good measure of evidence regarding mode of hypothesis. I think that's okay. So those are all those things, and now I hope that you will be treating p-value with like a lot, with a long stick, and then think, okay, let's be careful with those ones. Russ talked about p-hacking. I just want to add a couple of things to what he said. First of all, I love the way it was discovered. And the way it was discovered is also what Simonson, like a long time ago, was to actually look at the literature. And actually, in my lab, we're doing quite a bit of literature mining aspect, and I think that's it is very useful and can be extremely illuminating in many things. And I love the fact that that's what they did for kind of realizing what the p-hacking was. And I'm sure that's because they read articles thinking, okay, there's the p-value of that doesn't sound right or doesn't sound true, and therefore they started to dig into those things. The way they did it is to look at the method section of a very large number of articles, and then simulate some null data, and then apply the same method that were applied in those method sections that were reported. Okay, so those were reported methods. Applied those methods to the null data. So the methods were, we dropped this condition because we thought it wasn't the right thing to do, or we added 20 subjects to our group because we didn't have enough power, or all those methods that were actually reported in method section in articles, right? So they took all those things and they said, okay, we are going to take null data and apply those methods and how people analyze those data. And then they realized that for those data, I don't think I have the slide that show you the breakdown on which methods. For instance, there's adding an interaction in the model, there's dropping a condition, there's those sort of things. And then when they applied those things, they realized, on null data, this is giving us much greater type 1 error that the one we set for the test. And it was just purely empirical. It was just purely taking the literature and studying the literature, the method. And again, this is the reported things, so God knows what the non-reported things are, right? And that was very interesting to see. There is actually now a p-hacking test. So if you're interested in the field of research, you can look at the distribution of p-values in that field of that set of articles. Let's say there's a field of research. You take all those articles and then you look at the p-values of those articles, right? And that's it's fantastic because then usually what you expect, if there is signal in the things, the p-value should be very small, and then they be growing. And if there's no signal, what the p-value should look like. They should look like uniform, right? Okay. If there is no signal, that's fine. If there is some signal, we should have a p-value, a larger number of p-values that are very small than compared to p-values that are kind of larger. But if you look at what the p-values are between, let's say, 0 and 0.05, what you see in usually is kind of a growth towards from 0 towards the 0.05. So basically, there's way more p-values that are close to 0.05 than p-values that are kind of smaller or even uniform. So that you can do a test, say, okay, how different is that distribution from a uniform distribution? And you can say, okay, that field is actually p-hacking because you shouldn't have that this kind of distribution of p-values in the So that's interesting because it kind of gives us some reflection and some means of how to okay, we should now put some attention in that problem. So what are the solutions? I think we already mentioned a couple of times. Pre-registration is definitely the solution. There was some funny stories, but when I was at Berkeley, actually came up at this article in some journal say, okay, that journal, we're now banning p-value. That was funny because obviously it's a bit silly and it's not going to work. But it was quite cool to see. There's also statisticians that say, okay, let's change alpha. This is because alpha is too small, is too big. Let's put it at 0.005 rather than 0.05, and but obviously it doesn't work. But the important thing is that just complement all those things with confidence interval, all those things, because that's there. Still thinking of the literature and the sort of aspect, and I think I want to talk a bit more about the file effect, which is a very old effect. It's been seen so the p-values are coming from the 30s. That effect was detected and seen by in the 80s. And I think the thing that is really I mean, that's a sociological problem. Most journals will not ask for will ask for new finding. The finding must be surviving some statistical threshold. That gives some evidence. P-values are abused for that threshold, and the finding with a p-value of less than 0.5% is not going to be easily published. It's going to be super hard to publish something that says, hey, I had 50 subjects, I find a p-value of 0.2. I think this is an interesting to put in the literature because whatever. It's going to be tough. You're not going to go through the best journal for sure. This, I think you should have that picture in mind. Whenever you read the literature, is the distribution of z-value in I think a million of articles. So I think that's just a very nice illustration of the problem. Basically, that means that there is that a huge number, possibly a huge number of studies that are should be filling that gap, and because that is not a natural distribution, right? So I think that's it's fascinating. Maybe some of it is due to the fact that you are only testing things that are going to be significant. But I think most of it is just due to the file effect, or there must be the file effect must have a huge impact on this distribution. I love that distribution. I think it's actually quite funny that it's also shifted to the right because it's and what's the solution to that? And pre-registration is also the solution to that, because I've actually experimented once in the lab with the pre-registration. It's actually quite cool because it's so calming and and good in terms of what the kind of work you can do if you have put the plans and submitted your plans to a journal, and the journal said, yes, we're going to publish that, whatever you find, and that is such a good, place to work, because, you don't have to be stressed about what you find. You just want to find, to do the things properly and the most correctly, and then, this is it. I think it's a very, it's a great way to work. And not that many journals at the moment are actually accepting pre-registration. An increasing number is still a minority. And I think hopefully with more education and more advocacy, we will get more journals to accept pre-registration. Maybe if they don't, maybe send them that picture. I don't know. So, yeah. So one aspect, which is a very important aspect, is that you say, okay, why do you have a null result? Is it because actually there is nothing to, the effect size is super small or zero, or is it just because I don't have enough capacity of detecting it? And so the only null result, and if I'm an editor of journals, or reviewers, and that is a message that I give back, frequently. The only null result that is interesting and interpretable is a well-powered null result. So where you actually have a good capacity of detecting something if there is something. Otherwise, a null result can be, oh, I've taken 16 subjects and, I don't find anything. Okay, but, what does it mean? It means absolutely nothing. It doesn't mean that there's no effect. Doesn't mean that there's so that's a very, so please bear that in mind. I'm sure some of you know already, but that's a very critical thing that, null results are super important to push to the literature. They are also only visible if they are well-powered study. Witness curse was mentioned as well. So what is it? It's the fact that association passing a predetermined risk threshold will tend to overestimate the size of the effect. And I think Russ showed you the bottom data paper. And so what is important to see is that it's especially true when the sample size is small. So you're going to overestimate the effect size when it's small, and the threshold is stringent. So so in our field of neuroimaging and or even genetic, there's a very large number of multiple comparisons, so your threshold will be super high. Okay, so that super high threshold is going to impact the Wiener curves quite a lot, because you're going to detect only at that super high threshold. So that's an aspect. So it again occurs when there's a predefined threshold, small sample size, stringent type 1 error, and the impact of the literature as the effect size reported are super high compared to the actual effect size. This is just an illustration of that by Brian Nosek. Brian Nosek was the one starting the open science framework. So that's and some of the reason why he started the open science framework is actually that study. And that's on the x-axis, you have the replication effect. So Brian said they took 100-ish, bit less studies in psychology. So it was easier to replicate. So they replicated those. Many people replicated those 100 studies. It's kind of easier than in neuroimaging because usually it's 50 subjects that are students in the university, and just reaction time. And so those studies are easier to redo. I think that's one why they could do it quickly. And on the x-axis, you've got the replication effect size, and the y-axis, you've got the original effect size. And you see the replication effect size, all those red dots that are the non-significant effect size of all those studies have obviously had significant effect size. And the size of those things are the sample size. So they kind of show that but 40% of the effects were rated to have replicated. What I find fascinating, so first of all, you see the decrease of effect size in general. If you look at globally, the effect size has gone down. And I think the correlation with the original effect size is quite small, and I can't remember the loss of effect size that they got in replication, but it's quite significant if you look at the distributions there. The very interesting thing I thought was that actually, what can you say statistically about that result? You just display effect sizes that are found in replication studies versus the one that are found in the previous study. The real question is whether those things are actually different. They could be I don't think it's random because there's so many more non-replicated and smaller effect size, so that I think there's a neutral effect. But if you're a statistician, you would think, okay, how do I know that those things are different? And this is what this other study, I can't remember where it comes from. I think it's actually not properly published. It's only on archive. This other study is actually looking at whether those effect sizes between the original and replication were different. And they conclude that most of the time they can't say. There's not enough power to say whether they're different or not. And I thought that was fascinating because it casts a different light on that original study, and it makes the message a bit more complex. But in general, there are formulas and ways of correcting. If you look at an effect size in the literature, there are good statistical work that have been done. If you have to do a couple of hypotheses, yes, and you have to look at whether those are legitimate or not. but you can actually correct, for an effect size, that's with the, you can do a correction for that, for those things. So that's interesting to know. Especially, it's interesting. So effect size, I just want to, I talked about that. I should have put that a bit before. They often they come in many flavors, but the one that are called often raw effect size are simply like, for instance, difference of means. That would be like a raw effect size. What people call a standardized or Cohen's d effect size, and there's a number of variation on those things, but the principle is always the same, is that it's this raw effect size divided by the sort of variability of the data. Okay. And be careful with that. It's the variability of the data, not the variability of the mean. And that's and it's a very different thing. And the variability, if you look at the variability of the mean, then you have something that is looking like a z-value. Okay, so we've got those three kind of effect size level where the interesting aspect of the Cohen's d effect size, the one in the middle, is that it doesn't depend on the number of samples that you have. Okay, so that's a much more kind of transferable effect size. The z-value is not transferable because you don't, unless you know the number of subjects, unless you so you can't compare those things really unless you have the same number of subjects. Effect size, quick couple of notes on that. What is a good effect size to report? First of all, I think it has to be simple. If I tell you, I took the spectrum of that, SVD matrix, and I, took the, transformed that to be whatever. So this is my effect size, and it's a 2. And you're looking at that and say, okay, what does it mean? And it's going to be super hard to interpret. So interpretable with possibly, whenever with units, is one of the key things that you have to have in effect size. I don't know if Stephanie is here, but she's interested in effect size. So hopefully people from their lab will. The other thing is that it not only has to be interpretable with units, but hopefully it is also standard in your field. Okay, so like if in your imaging, for instance, we're looking at FD. Okay, FD is kind of it's kind of now people know how to compute it, what it means, and can interpret that. It almost has become a standard in terms of measuring movement. So that's so examples, percentage of variance, that's very simple, and it gives you a good interpretability aspect. So that's a good one. Correlation, that's a simple and good one. It's easy. It has the flaws, but at least people know about that. And standardized effect mean and so on. So what should be reported? Everything should be reported. Effect size, normalized, non-normalized. The most you put, the less there's capacity for not, for obfuscating something. I think that's all right. How much time do we have? 20 minutes. 30 minutes. Okay. I'll go over one thing. Maybe that's I don't know if you find it interesting, but this is to show that actually finding the effect size and finding the information from the papers are sometimes a very hard thing, because those reports are not standardized, and there's in a field it's going to be not always easy. This is a very old paper, so everybody has died, so that's fine to work on it. And the author, so there was one of the first imaging genetic paper that was shown, and a very fascinating. So it was the idea that if you take two populations with different allele on the for the serotonin transporter, and you show some fearful faces, for the population that has the short allele versus the population that has a long allele, you would find some difference in the bold signal in the amygdala. So that's in a very short, in one sentence. This is the paper. Okay. It's very impressive and fascinating result. It's and especially at the time when both functional MRI and the imaging genetic was was nascent. And the incredible thing that they actually report a replication. So they did a study on 14 subjects on one group and another 14 subjects on another group. And like I was blown away, like, you know, that at the time there was already like the idea of application. 14 subjects though is a bit of a problem, but you know, at the time there was at the time I remember there was this article by Carl Friesen saying that 16 is enough, like, you know, and you know, and yeah, anyways, that's another story for Pierre time. But the thing is that they report in their paper mean of you know, a short allele group is 0.23, mean of the Bolt signal in the amygdala is you know, long allele is 0.03, standard deviation of mean 1 is this number, standard deviation of mean 2 is this number, and these are the sample size. How do you compute the effect size, and what kind of effect size can you compute with that? So that's not, you know, like, let me go through it quickly. Well, first you get the standard deviation of the mean, and then you start moving backward and you get, okay, can I get the standard deviation of the data with the standard deviation of the mean? Because you know the sample size, that's possible. So you go for there, you get the standard deviation of the data, you know, collapse the two standard deviation of the two groups, that's fine. And then from there, you can say, okay, I've got the row difference of the mean 1, mean 2, and the standard deviation of the data, or an estimation of it. And then you find a coherence D of 1.05. So if you look at the literature, if you look, you know, like, you know, biology literature and things like that, standard D of one is a very strong effect size. Okay, that's you know, so you know, I can accept that, you know, like, you know, allele will actually, you know, influence the Bolt response in the amygdala. Whether it can influence a Bolt response with, you know, an effect size of 1 is, you know, like if you're a scientist with a bit of a, you know, effect size ideas, then you're kind of starting to question things. So what I did, the next thing was thinking, okay, can I compute the percentage of variance explained? And it's not maybe as easy, but it's not too complicated. You kind of write a linear model with the, you know, what is the model. So it's just, you know, the estimated difference of the mean, which that's the average of that plus the residual. You compute the total summa square, and then you compute the summa square of the actual effect. It's not that complicated. It's like, you know, it's really something that you, I think a little bit of basic stat and you can do. It's just you have to, you know, think of it and, you know, doing it once or twice to make it comfortable. And you find, like, you know, 40% of the variance of the Bolt signal is explained by that allele. And then, you know, if you're like, you know, I think it was Russ saying, like, I think the most biggest the signal that when you're moving hands or, like, you know, flashing signal in the retina, the biggest thing you find with Bolt is about, you know, 3-5%. Like, you know, it's so that's, you know, like, again, nothing against the authors, like, you know, this is like, you know, but it's just to give you a way of some tools to think about, you know, what you're reading and not and be skeptical. That, you know, I think it's as a scientist, be a skeptic person because of it. Another issue, which is you know, when the world of the UK Biobank and all those things, is that, you know, when you're starting to have like a super large, you know, like especially if you're looking at a p-value and things like that, is that at some stage, you know, everything becomes significant. Not significant because it's important, significant because it's statistically significant because there's so much n, the bigger n, and then the square root of n, and then you go, you know, like this is where it, you know, again, everything. So this is an example in the old paper where, you know, like, you know, even like white matter, mostly white matter, voxels will actually look at, have a Bonferroni corrected significant effect in that, in this inverse. I will finish, I won't finish with everything I have, but it doesn't matter, with a couple of things on power and PPV. Power, you know what power is now. It's just like, you know, the 1 minus the type 2 error, the risk of false negative. So that's how you represent it. It's always useful to have those distributions in your mind. Power is a key measure because, of course, without power, the study is not worth doing, that we know. Without good power, we've got, you know, inflated effect size, we've got Wiener's curse problem, we've got, like, you know, so power is a very important measure to have. Okay, so let's start from that statement. The second statement is super hard to compute. How many of you have tried to do some power analysis? 1, 2, 3, 4, maybe not that many, right? Not that many. And I would guess that, I would say the majority of you at least will probably have a setting for their project that might, warrant power analysis, or might be, power analysis would be beneficial. The problem is that, computing the power is super hard. You have to know H0, you have to know H1, or make hypotheses on those things. You have to know the effect size. You don't know, or if you look at the literature, it's a bias effect size. So you actually, so all those things are kind of not, you have to make decisions that you're not sure of. I still think that despite that, it's a super interesting and important exercise to go through, because at least you have a way of saying, okay, if I'm about right, this is about, the power that I will get. If I'm not right, if I really have underestimated that, this is what we're at. So giving that range of possibility is a super useful thing to have in a study, just, to have yourself, like, an inner understanding of where you're at. Yeah. You've seen that thing, and I don't want to go into it. There's a couple of other studies that are doing this sort of things. That's very interesting to see. And you've seen also the Marek, the Marek et al. Thing. But it's just to restate that, in neuroimaging, if you look at, how much the effect size is between those correlation between structural cortical thickness and the cognitive ability, or those kind of things, those are between minus 0.1 and 0.1, those are very small effect size, and those effect sizes are very variable if you just don't have enough subjects. I mean, those are the two messages that are, you could take from this. There's also a good set of, to be complete, like a good set of reaction to that paper that have been published in Aperture, actually, that have, kind of giving some light on that things that are not always, as dire as this paper was showing. And you also seen that I don't actually still understand that figure very well, but that is showing by Gael Veroko, good colleague and friend of mine, showing that if you look at the machine learning and the accuracy that you get on the, let's say, detection of diagnosis, a small sample size will actually give you a higher accuracy on the diagnosis. And why is that the case is interesting to dig into, but it doesn't seem to be always the case, by the way. But it could be some methodological error, it could be some other more diverse population, therefore harder problem. But in theory, that should not happen, and that's very interesting to see that happening. And I'm still a bit thinking about what are the key aspect that makes that figure real. Last thing I will talk about is something called the positive predictive value. And again, Russ mentioned that already. That's a very interesting concept, which is the positive predictive value is, so if you're doing some epidemiology, that's one of the first things you will learn about, because this is an important concept for tests, like COVID tests, all those things like that. It's the probability that, but in our kind of a hypothesis testing and scientific hypothesis testing framework, the positive predictive value is the probability that alternative hypothesis is true, knowing that the test is significant. So I have a significant test with a certain type 1 error. What is the likelihood that my hypothesis is true? Okay. So first of all, you have to require that the hypothesis is a random object. So that's like a little bit of a mental kind of a shift to do. But there is a very simple formula to actually compute the PPV, and I won't describe you how you get to that formula, but I've put that in the slide, and just to show you that it is not difficult. I think it's fun to see that you can get to that easily. By the way, you can't get to that easily with that paper. It's the most difficult paper to read, or to to extract the formula and to say, okay, what are those things? That's not an easy paper to but you can do it in a simple way. And the PPV is this funny function between power, the odd ratio of the hypothesis, which is basically the probability of the alternative divided the probability of the null. Okay, so let's say you have a very likely null and an unlikely, like an alternative that would be a small r, and divided by the same thing plus alpha, which is the type 1 error. So I found that formula fantastic because it's a very simple formula for bringing the three concepts together of what is the likelihood of those hypotheses prior, and what is my capacity of detection and what is my risk of error, and you bind that together into one formula. I will skip that. PPV, if power is difficult to compute, PPV is even worse because you need the prior probability of the alternative and the null. So that's even worse, but it's still also very interesting to compute. I'll skip the Bayesian thing and how you derive it. Please have a look; it's fun. The thing I want to show is what is PPV as a function of power with some kind of a standard risk of error. So with 5% risk of error, with an odd ratio of 0.2, which is okay, there's 5 more chance that the null is true than the alternative is. Okay, that's you can play with that number as well. PPV is, let's say, for 80% power, you have almost like 80% chance that your alternative is true, which is good. So if you have a significant test, 80% power, 5% type 1 error, then you kind of have a good chance that the hypothesis is true. Not that it is always true, like it's always but if we are, with the more like the classical, I would say, p hacking aspect, and in fact, it's not 5%, but it's 30% risk of error. This is how it looks like. So now, even with a good power, with 80% power, your likelihood that your alternative is true is dropped to 1/3, a third of that. So it's a very fascinating see how what are the important numbers there, and to have a look at those things. Yeah, this is another. And just to finish, it's interesting to also link those epidemiological concepts to machine learning concepts. So PPV in epidemiology is that, or like in the scientific, in this kind of a setting, is actually the precision in machine learning. So it's if you look at those formula, this is a power and odd ratio. So it's you kind of decipher by the one that are the positive and the negative, and then you just look at you just plug the numbers, and this is just the precision in machine learning. So I think relating those concepts is also, I think, useful. All right, so it's hard to estimate power. It's even harder to estimate PPV, and it's still a very, very useful exercise, and I would like to suggest that you do it. And I will skip the rest and hope for some discussion and questions. And there's a number of things that I haven't talked about. So I'll talk about what I haven't talked about, which is some of the consequences, and then how do we deal with that problem. But I think there has been some discussion with us already, and there can be some discussion now about that. So thank you.
So you had mentioned earlier about talking about the p-values and how, of course, one of the biggest ways to mitigate MSP hacking would be to
Register.
Yeah. You had also briefly mentioned how it might not be a good idea to change the alpha threshold away from 0.05. Although I do know that that's been a pretty big controversy within some research fields already. Can you speak more to that about that controversy?
I don't think it was. I mean, I'm not saying it's a bad idea to have a higher threshold. First of all, I mean I would say the opposite side of that proposal is first of all, it's going to be less sensitive. So we're going to miss some true positive where So that's one of the things. Secondly, we basically won't be able to actually do some experiments, so like because that's just like too. So those are the kind of it's just like the p-value, the threshold, the 0.05 threshold is completely arbitrary. Much better would be to think, okay, what is the consequence of a false detection, and what is the consequence of a negative, not detecting, and set the p-value as a function of those things, and think about what are the consequences and the risk. That than trying to set up like a higher threshold or lower threshold. Like I think that's more like my kind of a thinking of that. The other aspect is that it's super unlikely to work. I mean, maybe a small community will set a standard, but like in general, it's going to be like really community driven. I think, for instance, the genomic community, like and for the GWAS, for a long time had variation of their threshold for detecting you had this talk this morning by Jennifer, and they say finally set up like something that is like more visible at I think 5 to the 10 to minus 8 or something like that. Is their threshold, so it does happen, but it's I think the problem, the fundamental problem is that you have to think of what is the consequences of a true positive and true negative.
Yeah, can I ask a follow-up question?
Sure.
So with that in mind, keep in mind like how it should be arbitrary. Does it come with a bit of statistical naivety from me, but would it be wise to kind of set the alpha level depending on the sample size, such that maybe have a more conservative alpha for like very large sample sizes, and like maybe have it a bit more linear, quantified, also might still
that is an interesting question. I don't think it would be wise because the consequence is that you're going to have a lower threshold for like the small sample size, right? So depending on but I think it's the good response is you have to look at the effect size. You can't, the effect size is the thing you should look at, and the distribution of the effect size. And whenever you can do some resampling or and to have a visible estimate of the distribution of those effect size, that's the thing that you should be looking at, rather than whether and then maybe set the things in there. Yeah.
Question on Zoom from Tomas. Tomas, if you can hear me, go ahead.
Sorry, got it. Hello, thank you for that. You mentioned that we should choose effect sizes based on such that they have some biological relevance.
Yeah.
I'm thinking, how are we going to get here if we assume that the brain does everything in a net, orchestrating a network of areas and everything working together? How are we going to get to region-specific, network-specific, biologically relevant effect sizes?
Yeah, that's a very good question. And I think there's actually that's something that I was talking with Stephanie yesterday night, and she has a good project. That's something I thought of, a long time ago that would be a good project, and she's actually doing it, which is basically having an inventory of those effect size. So and that's super hard because you're mentioning different regions, different network, different population, but there's also different pipelines. There's there's so many source of variation, but having a resource where you can try to find, okay, what's my closest example to what I'm looking at, that's and again, I don't think it'd be like one gigantic repository for all effect sizes in the world, but in your imaging network analysis, where can we put some standards for those effect size on a good data set, and I think that has a reasonable chance of success and of being very useful. Yeah, there's no magic, a way of doing it. but actually it would be also a community resource that people can say, hey, I haven't found the same sort of effect sizes, and then people will start to think, okay, why is the case and what's the so I think it would be a very useful kind of a community resource if we can say those are all the factors, like population, pipeline, atlas used, like a way of measuring the connectivity and other things. And this is what I found in terms of effect sizes.
So my favorite when we discussing science and electrician, one of my professors mentioned that although she's very pro open science, she doesn't believe that every study should be pre-registered. And I was wondering if you thoughts on that.
So the question is, should every study be pre-registered? So pre-registration is mostly useful for hypothesis testing. Like, it's clearly like this is the kind of application of it. If you're thinking about something which is very exploratory, or if you're building something, or if you're like, there's many other things in science and just, hypothesis driven questions, then yes, I agree that that's not as useful. It is still extremely useful for yourself. It may not be as useful in terms of like pushing the paper out in the in the literature when when there's a non-significant p-value, but it's useful as you said, as okay, this is what I plan for my study, and this and I'm going to think in advance, and I'm going to not only think in advance but give that to people to give me feedback on that. So that's something that happens informally or formally between maybe with your supervisor, or but putting that and as almost like a formal thing that you can say pre-register for yourself and I think that's a useful exercise independently of whether you actually have to. But I agree with the fact that it's not all studies are meant for what we call pre-registered report, which is publishing publishing the pre-registration, so that's yeah. But the last part of the talk that I haven't done is really about communication of results, and I think to summarize in one sentence, we are still in a situation where most of our publishers are commercial enterprise, and we should shift towards a community or society, university, governed things, and even some it's fun to see I've seen some work in that direction, but thinking of okay, what is a new good publishing platform, and then that thing becomes an enterprise because you have to survive, and and there's commercial interest and all those things, and then it shifts to something else. I've got a couple of examples of that in my mind, so I have to be I think putting that in the hands of our university of societies is the thing that I believe is probably the safest thing for the benefit of the scientific community. Yeah. Cool. Thank you.